right, welcome to this video. This is 4.2a, which is one sample means with the t-distribution, which is sampling distribution of the sampling mean, right? So we're going to start with a few things here. Let me pull back up what I need. There it is. Okay. All right, there we go. So the sampling distributions that we've dealt with up to this point have been primarily normal, or we can approximate them to be normal. But if the sample size is too small, that normality, that curve kind of gets messed with a little bit and is less reliable. And the way that we deal with that is to change from a normal distribution to a t-distribution. So the t-distribution deals with small, it can be big sample sizes as well, but it was designed to correct for the errors that come with having a small sample size. And small here means less than 30. Right. If you have less than 30, right, you're most likely not going to fit the criteria, those three criteria, for your sample to be normal. And so we would then choose in favor of the t distribution instead. Very much like the normal distribution, the actual calculations are a nightmare, so we don't deal with those very much. But we will defer to a chart very similarly to what we did with our z-charts in the normal distribution. So for a single mean, right, and sometimes we'll deal with two means, but for now, let's talk about what happens if you have a single mean. Right, meaning one variable. You have one variable, you want to find out what the mean of that variable is, right? So for a single mean, we're going to use the standard error, SE, is going to be equal to this, the sigma, which you should know is the standard deviation of the population over the square root of n. Right? But again, typically, we don't know this. So instead, we would then say that this standard error is S over the square root of n, right? Where these are the typical sigma is the standard deviation of the population, and that lowercase s is the standard deviation of your sample. As you can imagine, the smaller your n gets, the larger that error is going to get, which would make sense because the smaller your n gets, the less likely you are to, the less sure you are about the accuracy of your mu to begin with. So the smaller n gets, the larger that standard error gets. Okay. So snag this right here. Where is it? I can't find it. There it is. Just steal this from the book and post it here. Yoink. All right, so this is the solid line. That solid blue line is the t distribution, and the dotted orange line is the normal. So you can see that the t distribution was designed with the same bell curve looking shape. It's approximately normal, right? But it is a little bit shorter, if you will, in the middle, and then the tails go out just a little bit longer. So what that does is it compensates for the lack of normality with a small sample size, and the probability of getting a value further from the mean in a t distribution is a little bit higher, right? And so that's the correction for the again, the small sample sizes that could skew the overall shape of your sample data. And then we have again, I'm going to steal this from the book so I don't have to write it. Have you all sit there and stare at me writing something for 40 minutes. All right. So these are the conditions, right, for when sampling distribution of X bar, which you should remember is the mean, right? For when that is approximately normal. So the data come from a random sample, a randomized experiment, that still holds, right? The sample observations are independent, that still holds. Your sample should be less than 5% of the overall population. And then the population is normal or the sample size is above 30, right? That's typically what we would say, well, this thing is normal. If it goes below that, right, if these conditions are met right down here, then the sampling distribution of X bar, or the mean, is approximately normal, with the mean mu and the standard error given by that function here. But the distribution, the t distribution, is what's called robust, which means that it takes into account those possible errors. Then the population can be considered normal as long as the sample data do not have extreme skewed or outliers. And then if that is the case, then our standard error is, again, the S over square root of n. If you recall, when we talked about the standard normal, it's been a while since I've written this, but normal, mu, and sigma, right? That is a normal distribution with two bits of information that tell you about its shape. It tells you the mean, and it tells you the standard deviation, and these two things are called parameters. For example, if I wrote, excuse me, normal 0, 1, that would be your standard, and I gotta check because now I'm feeling like I'm writing it backwards. All right, I got it right. So this would tell you that you have the standard normal, meaning that it's centered at 0, and it tells you how spread out it is. Your standard deviation is equal to 1, right? But if I wrote something else, like I said, well, what does normal 0 and 10 look like? You should know that, again, it's still centered at 0, but 10 is a much bigger number, so it describes the spread. And so it goes out much further in these tails. Likewise, if I had some normal that was like, say, 25 and 3, that means I know that this normal curve here is, that's a terrible normal curve, but it's centered not there. It's centered at 25. And that inflection point that looks like a terrible inflection point. One thing about what I'm drawing on is there's no way in hell I can ever draw anything that looks any good. But that standard deviation is 3. So it's 3 units from the middle to that inflection point. And it takes 2 parameters to describe that. But a t-distribution is always centered at 0. So it no longer relies on that parameter. It's not there. It's always 0. It's not a parameter anymore. It's a constant value. And so it only has one parameter. Right? And that parameter is called degrees of freedom. And the degrees of freedom of a sample is always just n minus 1. So it's not terribly hard. It's just 1 less than the number of samples or observations in your sample, right? And the more degrees of freedom we have, if you can see, hopefully you can see this okay. This very light blue starts right here and comes here. That's degrees of freedom being 1. It starts at a higher tail and comes to a lower peak. But as we get more and more and more, right, these guys start at a lower part of the tail, and the peak gets higher and higher, the more degrees of freedom you get, until we can say that normal curve right there is on the graph, right? And the higher your degrees of freedom get, the closer the t-distribution goes to the normal distribution. And so in fact, if the number of samples is large enough, it is the normal distribution, and it's pointless to use the t-distribution once again, because if you have, say, over 30 samples, you may as well just use your normal distribution, right? So again, excuse me, the larger the value of your degrees of freedom, which is abbreviated by just df, right, degrees of freedom, the greater that is, the more normal your distribution is anyway. So we have a chart here. So this is analogous to the Z chart, right? Where if you want to know the area in a tail, it'll tell you your t value based on your degrees of freedom. So if I have, let's say I have, or let's say I want to know the area. Well, let's find the t value. Let's do that. The t value. Why don't I have a blank? Oh, the t value for an area to the right. Right. So I'm talking about in the right tail. And I want that area to be, let's say 0. Or let's say in percentage, we can say, let's say 10%. So that is to say, wherever this value is, that's what I'm looking for, is this t value now, not a z value, but a t value. Close, they're very closely related, but I want this area here to be 10%. Right. If I just want it in one tail, I'm going to be looking at the one tail. I'm going to find the number that is associated with 10%, which is 0.100, right? So this is it. I need to know how many samples I have. So let's say I have a sample of, let's say 20 in my sample. Okay. So since my n is 20, right? N equals 20. My degrees of freedom are n minus 1, so that's 20 minus 1. So my degrees of freedom are 19. That tells me that I'm going to come to this row. I already know I'm in this column because I found one tail and the 10%, or the 0.1. So of course, the intersection of those two things tells me that my t-score is 1.33. All right, so it keeps zooming weird on me here, but what is a t-distribution with 18 degrees of freedom that has 2.5% of the values below it? So let me steal that chart again since I cleared everything. There it is. All right, so I want it's still a one-tailed test because I'm finding the percentage below a t-value. So drawing this out, I've got, my curves are getting worse and worse here. Yoop, that's whatever. That's supposed to be a normal-ish looking curve. So like, bear with me with this stuff. That's worse, whatever. But at some point, I'm going to find a t-value associated with some point here where that area to the left of it is just going to be 2.5%. So that is to say that my area is 0.025. I'm doing a one-tailed test, so I'm going to find that 0.025. So I know I'm in this column. I was told that I have 18 degrees of freedom, which corresponds to I have 19 sample size, right? So I'm going to find 18. That's this highlighted row. And so that t-value is 2.10. And then likewise, we can, is that an eraser? Yes. Say, perhaps, what is the t-value for, I mean, let me just reword it. Every time I word it that way, I get stuck. This, what value of the t-distribution the t-distribution with a sample size of 5 has 2% of values outside, right? Which is another way of saying to the left and or the right. Okay. So I'm looking at then a two-tailed test, right? And so my sample size is 5. Be careful with the difference between sample size and degrees of freedom. Here, you were given a sample size. Here, in this last one, you were given the number of degrees of freedom. I have a sample size of 5. That means my degrees of freedom is 4. And so I'm looking at the row with 4. And I'm looking for a 2% on my two-tail test. So I'm going to find what value corresponds to two-tail 2%, which is this guy right here. And so my value is the crosshairs there is 3.75. Okay. And I should note that this t value on the right here is 3.75. This one corresponds here to negative 3.75. And I didn't make the correction over here on the previous problem. But this t value is not 2.10. This value is negative 2.10 because this is that left-tailed test. So this should be negative 2.10 for that t value. Now, let me clean this up. You'll note as these degrees of freedom get larger and larger as we go down, right? This infinity right here corresponds to, you might recognize these numbers. Some of them should look familiar, but this corresponds to the z scores of a completely normal distribution, of a standard normal distribution, right? And so as we start off, these numbers get really large with, small degrees of freedom. But the more and more of those values, these numbers start to approach and get closer and closer to approximately normal distribution. In fact, the only difference on this chart between a value of 500 in your sample and the actual distribution is sitting right here. There's a 0.01 difference between a one-tailed of 0.5% area outside that value. All right. So again, this is really only to correct for those small values, and that's how it does it. All right, so, and again, I'm gonna, rather than writing this in terrible handwriting, I'll just be copying kind of the information that's important from the book here. But using the t-distribution, we're gonna use it for inference on the sample mean. When data come from a random sample or a randomized experiment, then observations are independent and approximately normal, right? So they still have to be not like humongously skewed, right? But observations can be considered approximately normal as long as there's not extreme skewedness or outliers. But we can relax the approximately normal condition even further as the sample size increases. For example, if the data distribution may be a little bit skewed when the sample size is at least 30. So even if you end up with something pretty skewed, if the more samples you get, that skew becomes less significant in the calculations. And then just like I kind of mostly said this stuff here, but Those 3 points in detail here, they come from a random sample or randomized experiment, right? We all know what that means. It's collected from observation units that are randomly selected. I mean, it's pretty self-explanatory. But the independence of observations is very much the same thing as before, 5% or smaller sample size of the population, right? But it's this one here, right? It's difficult to verify, it says here, with the small data sets. And so we look at a plot of the data for obvious departures from the normal model. So if there's some guy hanging out there way out in left field, it may skew your possible use of the distribution, the normal distribution. And then it says here to also consider whether any previous experiences alert us that the data may be not approximately normal. But again, since that t-distribution is robust, right, we relax this condition a bit so that skewing is tolerable in small amounts. And then a strong skew, if it's really skewed, you just have to up your n, your sample size, right? But if it's really skewed, you wouldn't be able to use a normal distribution. And so if you do have skew, even if you have a large sample, you can switch over, use a t-distribution, and that correction justifies the use of it. And I think that's that. I'm going to end this video here. This was 4 point something. This is 4.2a. I think I'm going to do a separate video for 4.2b so that these aren't humongously long and you can just watch one at a time or so. Anyway, thanks, and catch you on the next one.